Okay, so our next speaker is Professor Dmitry Karpov.
Thank you very much. My talk is about graph theory, and one of the most abstract parts of graph theory, the connectivity theory. Minimal k-connected graphs with minimal number of instances in the we use standard notations. The capital letters will denote the sets of vertices and edges of the graph G, and the small letters, corresponding small letters, will indicate the number of elements of the set. Yes, especially Vk is the number of vertices of the decay. Vector large is the maximum vertex degree. Let us proceed with the common definitions. Some definitions. A graph is k-connected if it has at least k plus 1 vertices and is connected and remains connected after deleting of any k minus 1 vertices. The restriction at least k plus 1 vertices is we need these restrictions because we want to avoid the case when any little graph is k-connected. Yes, any small graph is k-connected. It is, of course, it is not. A k-connected graph is called minimal if the of any vertex makes it not k-connected. Yes. This object, minimal k-connected graphs, was well studied in 60s, 70s, and 80s.
Say 4-connected, that is 3-connected.
Yes, of course, it's 3-connected, and it's not that the connectivity, the various connectivity is precisely k. It's at least k. Yes. Clearly, all vertices of a k-connected graph has a degree at least k. So it can explain the interest to the number of the vertices of degree k, of degree precisely k in a vertex k-connected graph. Of course, in a minimal k-connected graph, because any k-connected graph contains a minimal subgraph, and we will investigate the minimal subgraph. In 60s, Dirac and Plummer independently published two works, two papers on p-connected graphs, on minimal p-connected graphs. And it can be extracted from these papers, this inequality can be extracted from these papers. It is not formulated as a theorem here, but it is proved here. Several years ago, Gordon Butler, I think he is a classic in connectivity theory, proved a very strong result. It generalized the results of Plummer and Dirac. It's valid for any k. If we substitute k by 2 here, the result will be rather simple. But many of us, not only me and Butler, are interested in the precise constants. And this bound is tight. There are several examples of minimal k-connected graphs with precisely this, for which this inequality turns to equality. Yes? I'll show some examples on the next slide. And definition, the graph G is called extremal if this inequality turns to equality, if it has as small quantity of vertices of the k as is possible. Here is a picture for k is 2, but we can imagine such a construction for any k. Let us consider a tree with maximal degree k plus 1. Let us consider k copies of the tree T. Now we have 2 copies of this tree on the right side of the picture. And draw them in such manner that the corresponding vertices are near. Yes? They are joined with the line. Let A be a vertex of the tree T of degree J. Then to k copies of the vertex A, we add k plus 1 minus j new vertex of degree K. Here to the vertex of degree, here is the vertex of degree 1, and we have added 2 points of degree 2, yes? Here we can see a vertex of degree 2, and we add 1 new vertex of degree 2. And to the vertex of degree 3, on this picture, we add no vertices of degree 2. One can imagine such a construction, such a picture for greater car. It is not very difficult to see that the graph is k-connected and minimal. Any h which is in the vertex of degree k, of degree 2, or degree k for arbitrary k, of course cannot be deleted, yes? And the vertices at the edges of any copy of the tree 2 can be deleted too. One can count the number of vertices of this tree and the number of vertices of degree k. They are all new vertices, and assure that this graph is an external example which satisfies for which this equality is an equality. Of course, I think the first example which one can construct is such example for tree where the tree is a simple part. This is mother's example, showing that his inequality is his bound is tight. But here we can show that any such construction for any tree with maximum vertex degree k plus 1 is very true. And now here is our main theory, which is not so trivial as in this direction. Yes, any external minimum ignorant graph is a graph of type JKT for some tree T with the delta large at least k plus 1 with vertex degree at most k plus 1. Let me mention that the case k, 1, k equal to 1, is also, this is also true and trivial, because all minimal kinetic graphs are trees, and the external minimal kinetic graphs are simple paths, trees with 2 leaves, yes, 2 pendant vertices, and they are trees of they are graphs of such type because this construction add 2 new leaves for a simple function. So it is very true even for K1. It can be derived from area works for K2 and 3. It is the work of Oxley, 1982. He described an algorithm of constructing every external minimal graph for K2 and 3. For K2, we start with complete the bipartite graph K2, 3, and then several times repeat such operation. We take a vertex of degree 2 and substitute it by a complete bipartite graph K22, which is joined to the neighborhood of the substituted vertex by one partition. And the analogous construction is valid for K3, where we substitute a vertex of degree 3 by K33. Of course, here we start from K34. From our theorem, it can be derived from this method that the graph have type K, a type described in our theorem. But from theorem, of course, this facts are equivalent. We can derive such an algorithm for every tree car. It's very simple. Let me mention that K of these partitions, the this complete bipartite graph is a graph JKT for one vertex tree T. So we start with this graph, and this operation is an operation of adding a new pendant vertex to a tree. So the opposite operation is deleting a pendant vertex from a tree. Of course, if we know that every minimal external graph is a graph of type KGKT for some tree G, we can find a pendant vertex of the tree and delete it. It will be the inverse operation, yes? So this method of construction and our theorem are equivalent. Now I have some time, so I know that the talk about what is it is more interesting for most of you than some details of the proof, but I want to recover some details. Not the technical details, but some lemmas that I have used here and some pictures, show you some pictures. These are the notations. We shall consider the two sets of subsets of vertices. Vk are always of the degree k, and Vk plus 1 are vertices of degree at least k plus 1. Let ek large and small denote the set of all edges between these vertices and their number respectively. And here the set of edges is ek plus 1 and gk plus 1 is the induced subgraph on this set. We shall investigate this subgraph. At first, some any more definition which must be completed with a picture. What means that any H cannot be deleted preserving the K connectivity. It means that for any H we can find chi K minus 1 vertices, that this set of 1 H and chi minus 1 vertices is a cut set, or the deleting of these vertices and H makes the graph disconnected. Let us define a cut as a k-element set of vertices and edges that contains at least one edge and which deleting makes the graph disconnected. The condition that the cut S contains at least one edge is important because each cut maybe it has more than one edge, but it divides the graph into exactly two connected components. Each of these components contains one end of the edge that belongs to the cut. Yes, because ending this edge makes the graph connected. If the cut set have no edges, it is not. So we should study cuts. We know that any edge belongs to a cut, and we shall study cuts that have exactly one edge and (-1 vertices. And this edge must be from a plus 1, must connect to vertices of at least plus 1, because the edges that that are incident to the vertices of degree k are not interesting for us. The treatment of any such edge makes the graph disconnected. Here are Mother's lemmas, two lemmas, lemma in the correlate for the mother. About graphs. Let we have two edges, AB and AC, that connect the vertices of degree at least k plus 1. And S and T are such cuts for them. We shall denote by R the set of all such cuts that contain one edge from E plus 1 and the k minus 1 vertices. Here are such cuts. And let A be a part. Not part. Let A be component of the graph J minus S that contains R, and C be a component from the graph J minus T that contains C. Then A is greater than C. So this component is greater than this one. The easy corollary from this gives us that the graph G plus 1 is a forest, because if it has a cycle of all edges of which belongs to the set E plus 1, then such strong inequality cannot be varied over the cycle. It leads us to the contradiction that A is strongly greater than A. And here is a simple combinatorial inequality. Let C be the number of connected components of the graph Gk plus 1, and Ek is the number of edges between two vertices of degree k. Then we can estimate the number of vertices of degree k in such manner. This proof is very easy, very simple. We must only count the edges between these two sets. If we count them and their quantity and estimate it from two sides, we can see that the number of these edges is at least k multiplied by k because this number of edges is edges between these vertices, yes? And here the graph inside this set is a collection of C trees. So this additional constant appears. Mother's inequality follows from this one, this lemma. What is the minimum magnetic graph? If we know that this inequality is valid, it is a graph where C, number of magnetic components of G plus 1 plus number of these edges is exactly k, and all vertex degrees are k and k plus 1. Because in this inequality, if we count, when we count these edges each vertex of degree k plus 2 or greater gives us the strong inequality. And if we substitute this by k, we have the mother's inequality. So in what follows, we must investigate and study all the graphs with such that satisfy such condition. I have some time. In this picture, we show our new instrument to study cuts. It was an instrument that the mother didn't have. We define independent and dependent cuts. We consider only cuts from the set R with one edge connected to vertices of degree at least k plus 1 and countless vertices. They can be independent or dependent. They're independent if one part, one component, part of S are component joined with the vertices of cut S. So the cuts are independent if one part, if such inclusion, if the notations may be chosen as, in such manner that these inclusions are true. See this picture, it is more interesting than the definition. And here we show dependent cuts that cut each other, and independent cuts do not cut each other. If the cuts are independent, then their structure can be indicated by a tree. It is very convenient to work with tree structure. And if they are dependent, that cannot be indicated by a tree. So our main lemma is here. If G is an external minimal k-connected graph, then we can choose a set of pairless independent cuts that contain all edges of E plus 1. If we choose such a set, after that we can use the tree structure and study the leaf components, dependent components of this tree, and it will give us what we want. But this lemma is not very easy. It is rather easy for k at least 4, but for k greater 5 and greater, it is rather complicated. And the first step of proof was most complicated for me. The first is to show that for any cut of S, both components of the graph G minus S, after deleting the set S, has at least k by 2 vertices, is half of k vertices. Of course, there are minimal graphs which do not satisfy this condition, but then we can prove that the number of edges between the vertices of the cut is greater than k, and the graph can be external. And then the next step of our proof, we must transform, we choose an arbitrary set of cuts that contain all edges of the set k plus 1. And we transform the cards in such manner that we want to have a pair of independent cards. And on this picture we show how to transform two cards. This picture is, this step is not valid whether we have, if we have a card with a small component which is less than k than half by k. But if we so we cannot use it for any minimal graph, only for extra one. Here is the cards S and T and the two edges. The cards are dependent, and we have such four components that they are intersection of the components from S and T. Yes, such four intersections, and we can prove it is not very difficult that one of these components satisfies such conditions that it is not empty and it is a component for a card of the size K that contains the edge B1, B2. Exactly this edge, not this. So we can substitute one of this, a certain one, no, the card T by a card that is independent to S. After we, with the help of several such operations, we can finally reach our goal and have the pairless independent cards. No time. The next step is such lemma. Rather more trivial than previous. Short picture. Here is our independent cards. Let us see any of them. It have k minus 1 vertices and 1 edge. The graph is a collection of some trees. It's a forest, maybe with such trees. Then one tree cannot contain two elements of one card. It can contain this edge or one of these vertices, but not both edge and vertex and not two vertices. It is rather trivial if we have the tree structure. These components are included in each other in any direction of the tree. Yes, so it is rather lucid. After that, we pay attention to the minimal up to inclusion components, corrective components, the minimal component which correspond to the pendant vertices of this tree structure, and show that such a pendant component is a complete bipartite graph with partition K and K. It is the same picture as we have in the very beginning of the talk, but in the opposite direction. In the opposite direction, we find such a construction. It is the end of our graph. It is the terminal component, and we substitute this subgraph complete with a vertex B of degree K. It is easy to show that if this is an external graph, this is 2. We can count its vertices of degrees K and all its vertices. And it satisfies our equality. Then we must show that this minimum K connect is not very difficult, and Hence, it is a graph of type G, K, T strip for G, T strip. Because it is small, and of course we consider the minimal graph for which it is not true. Yes, minimal count examples. Of course, this graph for this graph, everything is true, and it is of type curve 1. And then this graph is a graph GKT for a tree T, which can be obtained from this tree by adding a new pendant vertices, by adjoining a new pendant vertices. This is a new leaf. Yes. So we performed an operation from Oxley's work in the opposite direction. He did the same for the K2 and 3, but very often the statements which are not very difficult for small connectivity are rather complicated for arbitrary connectivity, arbitrary K.
Thank you for the interesting talk. Questions? If not, then thank you again. And, we